isolation. I told in my first talk that bearings are perhaps the first element which fail. Either the bearings themselves fail or the connections of the bearings with the bridges fail during earthquake. And base isolation devices are very similar to bearings. That's why we have clubbed bearings and base isolation. And sometimes there is a confusion. For example, in case of a elastomeric bearing, that whether it is acting like a bearing or like a base isolation, because same device can be used as bearing and the same device can also be used as base isolation device. So in which case we will be designing it like a bearing, and in which case we will be designing it like a base isolation. So those situations also need to be discussed. So I will talk about these two topics. So first of all, what is the role of bearings? Why do we need bearings in bridges? So are bearings essential in the bridges? Perhaps not, because we are having now integral bridges also. But the forces which may develop in integral bridges, particularly due to temperature and due to differential settlement, those can be very large. So when we are designing integral bridges, we have to take into account the additional forces which will develop due to temperature movement, and temperature movement, the forces due to temperature movement will depend upon the flexibility or stiffness of the substructure. If we have a tall substructure, a short span bridge with flexible substructure, in that case the effect of the temperature is going to be less. But if we have a long span bridge and connected with stiff piers, the short piers, the effect of the temperature force or temperature is going to be quite large, and it may be excessive, more than even what we will get from earthquake. So to relieve that type of movement which may occur due to temperature creep and shrinkage, that is our primary objective. Then same thing happens in case of differential settlement. Settlement of the foundation can always take place in soil. If that settlement is taking place uniformly, it is fine. But if there is a differential settlement and we have an integral bridge, then there will be excessive forces in the superstructure. So to avoid those forces, we can allow or we can release the movement due to this differential settlement by making our bridge determinate. So the bearings, the arrangement of the bearings is provided in such a way that it becomes a non-redundant or determinate structure, so that the effect of differential settlement is not causing any additional forces. So it can take a change shape under differential settlement such that no forces are generated or no forces are developed within the structure. So that is the very purpose of bearings. So bearings relieve the structure from this type of forces. And when the dead load and live load is applied, the superstructure deflects. And when it is deflecting, there is a rotation at the end. That rotation at the end is to be allowed. Otherwise, it will act as fixed beam, and we will have large moments at the ends. So to allow that rotation, we provide bearings. And I already told that differential settlement is one of the major cause of forces in the superstructure. We can relieve those by providing bearings. Then bearings have also to transfer the forces from superstructure to substructure. These have to transfer the vertical force due to dead load, live load, wind load. Vertical component of wind load is there, vertical component of earthquake load is there. So the vertical components of the earthquake force are to be transferred to the substructure through these bearings. At the same time, the horizontal components of wind and earthquake. So wind and earthquake can cause horizontal components, or rather have primarily horizontal components. So those horizontal components of forces are also to be transferred through these bearings. So different types of bearings based on the first objective, that elongation in the longitudinal direction or contraction in the longitudinal direction due to temperature. The temperature movement in the longitudinal direction is to be relieved. And for that, the most simple arrangement is that we have two plates which can slide on each other. So this is the sliding bearing, simple sliding bearing. So when the surfaces are flat, the rotation will not be allowed. Rotation will not be free. We have to have some other arrangement to allow the rotation, or the rotation is really small. So this, what you see here, this is a longitudinally guided sliding bearing. So this bearing will allow sliding movement in the longitudinal direction, but in the transverse direction, it is stopped. So the surface which is sliding, that has to be stainless steel so that there is no corrosion and the friction is to be minimized. Sometimes we can keep a Teflon layer here, PTFE layer here in between these two so that the friction is minimized and sliding can occur easily. So this is only to allow sliding. We can extend it further. Here we are allowing rotation, but not the translation. So longitudinal translation is not allowed. So this is a rocker bearing. So in rocker bearing, rotation can take place, but longitudinal movement cannot. So what you see here, there is a convex surface at the bottom, and at the top, there is a flat surface. So this flat surface can rotate above this concave surface. So rotation is possible, but this type of pins are provided along the center line of this bearing. So horizontal movement is not possible. So it is really like a pin bearing. So where rotation is allowed, but the translation in longitudinal as well as horizontal direction is not allowed. And what you see here, these are the anchors which are to be anchored into the concrete. So into the bottom concrete, into the pier cap, and the top anchor here, the top plate will be anchored into the superstructure and bottom plate will be anchored into the pier cap. So this type of bearing allows rotation. So this is a pin bearing. Another type of pin bearing, which is very similar to what we generally show in our diagrams. So we have two sets of plates which are arranged in between each other, and then there is a pin here. So there is pin. This pin will transfer the horizontal and vertical force, but the rotation will be allowed through this. Now you can see here that the rotation is allowed only about transverse axis. So whatever rotation is taking place in the longitudinal plane, that rotation will be transferred. And no movement can take place either in vertical direction or horizontal direction or translational. I mean longitudinal or translational direction. No displacement is permitted. Only rotation can take place. So it can transfer the vertical force as well as horizontal force, both. Then we have a bearing which we call rocker cum roller bearing, which has the action of rocker as well as roller. So it is like a what we provide as a roller support in our beam, simply supported beam. So it has combination of the rocker bearing which we have seen earlier, and below that some rollers are provided. So it releases the longitudinal translation as well as rotation. So rotation can also take place. At the same time, the elongation or contraction in the longitudinal direction can also take place. So this can transfer only vertical load. It can't transfer horizontal force, and it can't transfer moment. Then another way of doing that, because the problem with all these bearings which I have shown so far is corrosion. And when the corrosion occurs, these becomes fixed, and rotation or translation which we are anticipating cannot take place. So after some time, there are problems in functioning of these bearings. These get clogged also because of the dirt going into it, and movement becomes very difficult. If it is not under proper maintenance, it will become difficult. Operation of these will be difficult after some time. So to avoid that, we have another type of bearing, what we call pot bearing. So in pot bearing, we have a elastomeric pad here. So what we see, this is the elastomeric pad which is confined inside the cylinder. So elastomeric pad, it is flexible. When you compress it, it bulges in the horizontal direction, but when it is confined, then this bulging cannot take place, and in that case it has sufficient stiffness, but still it is flexible enough to allow rotation. So if this top plate wants to rotate in any direction, this will allow a rotation. And because the top plate is inside a bottom cylinder, so we can see that the movement is not possible. So movement in the longitudinal or transverse direction is not possible, but the rotation is possible. So here the rotation is not taking place on a curved surface. Rather, it is taking place on a pad of elastomer. So an elastomeric pad is provided, and under pressure this elastomeric pad behaves like a fluid, a very viscous fluid, and when it is pressed on one side, it gets compressed here and it bulges here. So that type of flow can take place here, and very easily it can rotate in any direction. So this is one of very commonly used bearing currently, but people have reported some maintenance related issues with this type of bearing also. Uh, in use for 20-30 years, after that it becomes very stiff and it is not behaving the way it has been designed. So it does not allow the rotation as freely. So replacement may be required, especially replacement of this elastomeric pad may be required after some time. So that problem is happening here also. But in along with these bearings, I mean, just to show you a size, just to show what can be the size of such pod bearings. So this is a typical photo I have downloaded from internet. So you can see relative to the human size, what is the size of this bearing. So really for large size bearing, to large size bridges, we can have large such bearings which have a lot of capacity, and it will allow the rotation of the bridge. And if the size of the bridge is so large, we can understand that the rotation is also going to be significant. Then we can add a sliding surface to the pod bearing. So at the bottom we have the pod bearing. The purpose of the pod bearing is to allow the rotation. So it will allow rotation in any direction. And then we have a PTFE sheet at the top. So we have a stainless steel plate, and below that stainless steel plate we have a layer of PTFE. And this PTFE layer here, so PTFE has very low, it is like a lubricant. So it has very low friction with stainless steel. So it can allow easy sliding. So here the sliding can take place easily, and rotation will come from this elastomeric pad. So both the actions, rotation as well as sliding. So it is something like rocker and roller bearing, which has been obtained using part of elastomeric pad and a sheet of PTFE. So that PTFE sheet is allowing the sliding. So both rotation as well as the translation are released here. It can transfer the vertical load, but it cannot transfer the horizontal force and the moment. It will allow sliding against those. Now, this is a guided sliding bearing. So this is pod PTFE bearing only, but it can its movement can be restrained in one direction. For example, here it can rotate about the axis outside the plane of the screen. So it can rotate about that axis because the elastomeric pad is provided. So this elastomeric pad can deform, and due to that deformation, rotation is possible. Then sliding is possible perpendicular to the plane of the screen. But along in the plane of the screen, if it wants to slide in this direction, then there is a guide in the center which will not allow it to move. So we have a guide here. This bottom plate has a protruded element here which is guiding this, so it can't move in the horizontal direction in the plane of the screen, but perpendicular to the plane of the screen it can move. And here we have this PTFE layer. So two PTFE plates are there, both sides of this guide, so it can slide over those. So it can slide in one direction and it can rotate also, but one direction it is resting. So sometimes we want to transfer the transverse force through a bearing, the earthquake force or wind force in the transverse direction we want to transfer, but we don't want to restrain the longitudinal movement. In that case, we can use this. And in some cases, we also want to restrain, for example, at one end of the span, at one pier, we want to restrain the longitudinal movement. But the transverse movement, now in case of a wide bridge, the transverse movement can also be significant. So if we try to restrain that, the bearing will be subjected to very large forces. So we allow the translation in the transverse direction, but we transfer the forces in the longitudinal direction. Then the same bearing can be provided there also at an angle of 90 degree. So we can arrange this guiding mechanism in such a way that it can act as a longitudinally guided bearing or a transversely guided bearing. Longitudinally guided bearings will allow the displacement in longitudinal direction, but it will transfer the force in the transverse direction. Whereas a transversely guided bearing will allow the movement in the transverse direction, but it will transfer the force in the longitudinal direction. So depending on the requirement, which force we want to transfer and which movement we want to release, we can arrange these bearings. Now, problem, as I said, that with this elastomeric pad, which is allowing the rotation, there are problems. So to overcome that, recently people have started using spherical bearing. So it is a combination of the initial metallic bearings as well as the elastomeric bearings. So what is done here, we have a concave surface on which there is a concave there is an articulated concave surface which can move within this concave surface. So this convex surface will move within this. So it can accommodate rotation. So when rotation occurs, it simply moves along this. So the rotation will take place about the center. So this is the radius of this concave surface. So at the center of this concave surface, about that the rotation will take place. So we can allow this type of arrangement can allow rotation, but it will not allow the movement. So it can't slip. So it and there are guides provided. So it can't move, but it can allow the rotation. And between the concave and convex surfaces which are metallic, we have a PTFE layer which acts as lubricant, so that controls the friction. So with minimal friction in pure metallic bearings, the problem was that after some time, due to corrosion, the both plates were getting welded, naturally welded, and the movement was difficult. So here between the two surfaces, a PTFE plate is provided, which can allow easy friction, easy sliding for long time. So that type of arrangement we have, and then at the top of it, we can also have a PTFE layer, and this PTFE layer, and it is sliding against this stainless steel plate. So the sliding is also possible. So we can have all the three types of uh, motions or all the three types of possibilities. We can use it as just a pin bearing, which is allowing rotation but not allowing translation in any of the direction. In that case, these guides which are provided here, which you see here, so these guides are provided in both the directions, in longitudinal as well as transverse direction. So that will allow the rotation, but it will not allow movement in any direction. Okay. Then it can also act as longitudinally guided bearing. So in that case, these guides will be provided in the transverse direction, and movement along the longitudinal direction, the sliding movement in the longitudinal direction can take place in addition to rotation. So here I have just some photographs to show you the scale that these can also be developed for very large size. So depending on the requirement, how much force we want to transfer through these bearings can be produced in any size for any amount of force to be transferred. Now, another very common type of bearing is elastomeric bearing. In elastomeric bearing, again we have elastomers. Problem with elastomer is that when you apply compressive force to it, it bulges. So in case of pot bearing, we have taken care of that bulging by putting it inside a pot, inside a cylinder, so that it cannot bulge outward. And then the compression stiffness will be controlled. Now we can also use it as a pad, but in that pad we have these steel plates. So these steel plates are glued or vulcanized inside the rubber elastomer. And when the rubber is trying to expand, the elastomer is trying to expand in the lateral direction, these plates are confining it. So role of these steel plates, so there are alternate plates of rubber, steel, rubber, steel, like that. And the role of these steel plates is that these will confine this elastomer. And if I was using a elastomer pad without these steel plates, it will bulge and the vertical stiffness will be very less and a lot of vertical deformation can take place. So these steel plates allow horizontal movement. These steel plates also allow rotation, but these prevent the bulging of this elastomer and provide vertical stiffness because all our bearings have to transfer a vertical force. If you look at the structure, it is something like this. So we have rubber, and within the rubber we have steel shims or steel plates which are glued to this rubber, these rubber plates. And these rubber plates are acting as confinement. So when the rubber tries to bulge, these steel plates will confine, and then now here the bulging will take place only between these two plates, whatever is the single rubber plate, rubber slice side. So only that much deformation can take place. So it increases the stiffness in the vertical direction significantly. So it works like this. Suppose I was having a rubber block only and I apply a vertical force to this, it will deform a lot in vertical direction and it will bulge in the outward direction. But when I put these steel plates, then these steel plates will act as confinement and these plates of rubber will deform individually. And because these are confined at top and bottom and the height is less, we can see that the deformation is going to be less. So the vertical stiffness of this system is going to be much more than this system. Same thing in case of horizontal direction. In case of horizontal direction, it is unaffected. So whatever is the deformation taking place in the rubber block alone, same deformation can take place here because these steel plates can simply slide. These can simply move in the horizontal direction. These are not providing any restraint against the shear deformation of the individual rubber plate. So it is not affecting the horizontal movement, which is important to us. We want to make these flexible in the horizontal direction, but we don't want to make it these to be very flexible in the vertical direction. So that is achieved by providing these plates, steel plates. In practical installation, you can see it looks like this. This is the cross section. So it looks like this. And here you can clearly see that where the steel plate is and under the load, how the rubber layer is bulging out. So you can see that the rubber layers are bulging out. If these steel plates were not there, it would have simply bulged together. And too much of bulging and too much of vertical deformation could have taken place. So these steel plates are preventing that bulging as a whole. Okay, so these are provided as I have shown in the previous figure also. So these are provided between the superstructure and substructure, and these are properly anchored. And these can provide all the actions. So these can release displacement in longitudinal direction. These can release the displacement in y direction, and these can also transfer because their stiffness is not zero. For example, when we are having a sliding surface, the stiffness is almost zero because the resistance these are providing is equal to the friction force, and the friction coefficient is quite reduced, especially by providing PTFE layer, which acts as lubricant. So by providing PTFE layer, we reduce the displacement, the resistance against horizontal displacement, and there the horizontal displacement is easy. Here is horizontal displacement is relatively free because these rubbers are flexible in horizontal direction. But at the same time, if required, these can also transfer the forces and these can allow the rotations also. So these bearings can be used in different ways. Sometimes we use these bearings only to release the displacements and rotations in the directions we desire. So that is the common role as a bearing. So these can be used as common bearing. And when we are using as common bearing, these should not transfer the load. In that case, the load is to be transferred by some other arrangement. By the side of these bearings, we may have to provide some stoppers, some reaction blocks, so that the forces get transferred directly through those reaction blocks. Horizontal forces, I am talking. Vertical force will be transferred by these bearings only. But in the horizontal direction, at one end of or at one end of the span or one pair of the span, we will uh, restrain the movement of the superstructure by providing adequate arrangement so that the forces are not transferred through the bearing. So forces will be transferred, the horizontal forces will be transferred through that additional arrangement which we are going to provide. In that case, that end where we are providing these restraints, that will act like a pin bearing. So it will act like a pin bearing where horizontal displacement is not allowed, but the rotation will be allowed. At the other end, we will not provide such restraint, so it will accommodate the displacement as well as rotation at the other end, and the horizontal force transmitted will be much small. So that's how these can be used as normal bearings. If I'm not providing those uh, stoppers here, restrainers here, or additional arrangement to transfer the load, then the force will also be transmitted, the horizontal force will also be transmitted through these bearings. And these bearings are going to deform a lot under that horizontal force because these are flexible elements. And in that case, it will act as base isolation. So we will talk later about base isolation, and then I will explain that when these are being designed as base isolation, then what precautions are needed. So the same bearings can be used as normal bearings, and these can also be used as base isolation bearings. Only difference is that when we are using these as normal bearings, at one end we have to provide additional arrangement to transfer the forces. These bearings should not be part of lateral load transmitting mechanism. So lateral load transfer from superstructure to substructure should not take place through these bearings. There should be a separate arrangement. If the lateral load transfer is taking place through these bearings, then there will be a special requirement for these bearings to be designed as base isolation. One more thing, when we are providing stoppers here, then this end of the superstructure will act like pin. And in that case, the flexibility of these bearings will not come into picture. These bearings at that end will be used only for providing rotation. So in that case, the structure will be designed, the bridge will be designed normally, assuming one end pin and the other end free. And the longitudinal direction, that mass will be lumped to one pier, where we are providing it to be pinned. At the other end, it will be supported in the transverse direction, but it will not be supported in the longitudinal direction. So it will be free to move in the longitudinal direction, but in the transverse direction again, we will provide stoppers. So it will act like our normal rocker roller bearing, and we will design with normal response reduction factor R. But when we are designing these same bearings without these stopper arrangements, then it is acting as base isolation. The period is going to increase in that case because the flexibility of the bearing will come into picture. So the period will increase, and due to that, the earthquake force will reduce. That is precisely the action of a base isolator. So it will act as a base isolator, but then it needs to be checked for the displacement which will occur here, and it should be safe under that displacement. And its quality should also be ensured to take care of that displacement. So we will talk again about these bearings when we will be talking about base isolation. Okay, so testing of these bearings is also easy. Generally, what we do, we test these bearings in pair. So you can see that one bearing at the top, another bearing at the bottom. It is subjected to a vertical load. So we put a jack in the vertical direction, apply the vertical reaction, whatever vertical reaction these are designed for, and then we can apply a horizontal force to test this. And this horizontal force will be equal to the horizontal capacity of two bearings. So 2 times H. So if H is the capacity of one bearing in horizontal direction, 2 times force we have to apply. The top and bottom plates will be fixed, and the central plate will move. So like that, we can test these bearings in pair. Now, these bearings, if I am considering normal neoprene bearings, or what we call low damping rubber bearings, so these are also having a hysteretic loop, but the size of this hysteretic loop is quite small. So these have what we call viscoelastic properties. So these dissipate some energy. It is not linear. It is not represented just by a line. So it is close to line, but there is a small hysteretic loop. So due to that, these are dissipating some energy, and these are having some damping. So that damping is of the order of 5 to 6%. So 5 to 6% damping, these can provide through energy dissipation. And energy dissipation depends upon the area of the stellaritic loop, because this is the energy, amount of the energy which is dissipated in each cycle. So we can calculate the equivalent damping. I will show the formula later. There is a simple formula 1 upon 4 pi ED over ES naught. So ED is the area of the stellaritic loop and ES naught is the area of the triangle. So if I join origin with this point, this triangle will form. So if I calculate area of that triangle, so that is the strain energy stored by equivalent linear system, equivalent elastic system. And the energy dissipated per cycle is area of this stellaritic loop. So if I take 1 upon 4 pi ED over ES naught, that will give me the equivalent damping, equivalent viscous damping for this energy dissipation. So some energy dissipation takes place through these LDR, low damping rubber elastomeric bearings also, but that is of the order of 5 to 6%. So practically it remains the same as we have been doing in case of normal structures. So these will be designed with normal response reduction factor. But when we are using these as base isolation, so not only these base isolators, but all other base isolators also, when we are providing, the structure will be designed for response reduction factor equal to 1. So the forces in the piers, foundation and the superstructure will be calculated considering R is equal to 1. So we assume that when we are providing base isolation, the structure will remain elastic. There will be no damage in our structure, and period will be elongated, so the total energy imparted to the structure will reduce, and that will be taken care of by the energy dissipation through these bearings. So the structure need not to dissipate any energy, and we will take R is equal to 1 in that case. Now, how the base isolation works. So I explained in my first class also that the base isolation works on the shape of the response spectrum, because the predominant frequency band in our ground motions which we are getting, so that can be seen from the shape of the response spectrum. So the predominant frequency range is between 0.1 second to 1 second, roughly in that range. Depending on the type of the soil, it may be 0.4 up to 0.4 second, it may be up to 0.6 second, 0.7 second, but definitely by 1 second, that predominant frequency range is over. So if I make the frequency of my structure far away from that predominant frequency band, either I make it very stiff or I make it very rigid. Sorry, I make it very stiff and rigid are the same. So I make it very stiff or I make it very flexible. So if I make it very rigid, then what happens? The response of the structure will be same as the response of the ground. So this is what we call zero period acceleration or ZPA. It will be equal to PGA. So it will be much less. You can see that it will be 1 upon 2.5 of the peak spectral acceleration. So if my structure is having its period of vibration between 0.1 second to let us say 6 second, so it will be in the peak spectral range. So force will be reduced by 2.5 times, but we can't reduce beyond that. Whatever stiffness we increase, the maximum reduction can be up to ZPA, zero period acceleration. But on the other hand, if I make my structure flexible, making the structure flexible is relatively easier. Making the structure rigid is difficult. For that, I have to put a lot of material, but making the structure flexible is easier. So one thing is that I can reduce the size of my pier, and then the structure, the bridge structure will become flexible, but then there will be problem due to large displacement, there will be period defects. So we don't do that, but we use special elements which have higher flexibility as compared to the piers. And due to that, the displacement is taking place in that flexible element. The piers are not deforming, so there is no issue of period defect there. But our those elements, additional elements which are providing the bearings or the isolation devices, the deformation is taking place. So we can see if the system is very flexible, the acceleration in the superstructure is going to be close to be zero. If it is very, very flexible, like the example I have taken a balloon and a thread, so if it is that type of system, then there will not be any transmission of the ground motion or the forces due to ground motion to the structure. But at the same time, the displacement will be large. So large ground displacement or large relative displacement with respect to ground will be taking place. And whatever device we are providing, that device should be capable of absorbing or catering to that much displacement. So this is the challenge in design of base isolators, that it should be able to cater to this much displacement. So large displacement is going to occur. If we look at in terms of acceleration and displacement, so on the rigid side, when I make it perfectly rigid, the displacement is going to be zero. By displacement, here we mean rigid, the relative displacement. So displacement between the superstructure and the ground, relative. So the structure will move along with the ground. So there is not going to be any relative displacement. So relative displacement will be zero, but the acceleration will be high. And this acceleration will remain constant for some time. And then after, when the flexibility increases, that means period increases, this force reduces. And at very flexible system, this will become zero, but the displacement will become maximum. So the displacement will go on increasing, the acceleration will go on reducing. We can also understand this from our response spectrum. So these are the response spectra used, for different codes. So shape is important. Shape in absolute values may differ from place to place, but what we can see here is that the shape is similar. And suppose my original structure is having a period of 0.5 second. So there, this value is something like 1.8 G. And if I increase the period to 2 seconds, so you can see that for the same curve, now this acceleration is 0.6 G. So it is reduced to 1/3. So, and if I increase the period further, I go to, let us say, 3 seconds, then it will become only 0.4 seconds. So as I increase the period, the acceleration which will be acting on the superstructure will go on reducing. And when the acceleration is reducing, the earthquake force is also reducing, because force is simply mass into acceleration. So by elongating the period, I can take advantage of detuning. So this detuning is making the frequency of my structure far away from the frequency of earthquake. So predominant frequency of the earthquake is in this range where we are getting the peak of the response spectrum. So this is the range in which we are getting the predominant frequencies. I said up to 1 second. So roughly up to this, you can see that this is the predominant frequency. But if you take your structure away from this for 2 seconds or 3 seconds or 4 seconds, you can see that the the force will go on reducing. And maximum advantage you get from 1 second to 2 seconds. In this range, you will get up to 2 seconds, you will get the maximum advantage. After that, the reduction is not that sharp. It is proportional to 1 upon t. So initially, it falls very rapidly with increase in t. Then it is not increasing with the same same pace. So the period we will generally, the period of the isolated system will keep in the range of 2 to 3 seconds. So in this range, we will get the maximum advantage. If we look at the displacement spectrum, we discuss the displacement spectrum also. We can obtain the displacement spectrum by multiplying as a spectral acceleration, which was there in the previous figure. If I multiply that by t square by 4 pi square, so I will get the displacement spectrum, and shape of the displacement spectrum to 4 seconds is like this. Initially, it is increasing cubic parabolically and then parabolically, and then it becomes a straight line. So it is going on increasing linearly with the period. So you can see that the displacement at 5-second period was much smaller, and here the displacement has increased. Okay, so it has increased roughly by 5 times. So at 0.5 second, this was 5 inches. Now here at 2 seconds, it is roughly 25 inches. So the displacement has increased roughly 5 times. The force reduced roughly to 1/3 when we have increased the period from 0.5 second to 2 seconds. So this displacement, increased displacement, that is to be carefully considered in our design. Now, in addition to dampers, we can also use damping. The advantage of damping is that it reduces the force because the damping, additional damping results in reduction of the overall shape of the responsive spectrum. So it is not only it is reducing the acceleration and hence the force, it reduces the displacement also. So we can see that due to damping, the displacement is also reduced. So due to some reason, if the displacement of my isolation device is coming out to be very large, for example, if I'm using elastomeric bearings or low damping rubber bearings, which have very low damping, so there the displacement will be higher. And to control that displacement, I can provide in parallel to the isolation device some damping device also. So damping device will help in reducing the displacement. So base isolation device will elongate the period, that will reduce the forces or acceleration. The damping device will reduce the acceleration as well as the displacement. So we can control the displacement by providing damping devices in parallel with the isolation device. So many a times the isolation device itself has sufficient damping. So in that case, we don't need any additional damping device, but in some cases, the damping device may also be required in addition to the isolation device. So as I said, low damping rubber has some hysteresis and it can dissipate some energy, but that energy dissipation is equivalent to 5 to 6% of damping. So it is not much. It is more or less same amount of damping which we are getting in our structures without any damper. But if we use a high damping rubber and natural rubber which we get from the plants, that is one of the high damping varieties of high damping rubber. So when we are having high damping rubber, the size of the hysteretic loop increases, and here we can get higher damping also. In addition to the flexibility, we will get damping as well. So this is the hysteretic loop, typical hysteretic loop of high damping rubber isolator. So if we use high damping rubber along with the elastomeric pad, then in addition to flexibility, we get the damping also, energy dissipation also. This will control the displacement of our structure. So we can calculate this damping factor beta, equivalent viscous damping factor beta, as like this: 1 upon 2 pi kh over k effective delta square. So AH is the shaded area. This whole of the shaded area is AH. This is the energy dissipated per cycle. So when one cycle, hysteretic cycle of low displacement is completed, this much energy gets converted into heat. So this energy gets dissipated, and K effective into delta square. So this is K effective into delta. This gives this force, and this force K effective into delta square, that is equal to the area of this rectangle. And you can see this area of rectangle is double of area of this triangle. So earlier I have given you 1 upon 4 ED over ES naught. So ED is equal to AH and ES naught is 1 upon 2 K effective into delta M. So here it is used 2 pi, but in place of 1 upon 2 K effective into delta square, it has been used K effective delta square. So this is the same which I have talked. This is equivalent to 1 upon 4 pi ED over ES naught. So this is a very useful formula which we can use to convert the energy dissipated by any device into equivalent damping. And once we know equivalent damping, we can read the response of that system from responsive spectrum. We have seen that responsive spectrum we can derive for any value of damping. So factors for converting responsive spectrum from one damping to another damping are also available. One such empirical relationship I will also provide in this talk. Now, another way of enhancing the energy dissipation capacity of low damping rubber elastomeric bearings is by providing a lat core. So lat core has very high ductility. So under lateral force, initially this lat core will remain elastic and it will provide stiffness. So stiffness will be provided by these rubber pad, around this as well as this lead core till the lead core is yielding. So once the lead core yields, it starts behaving non-linearly. So this elastomeric pad, this remains elastic throughout the movement, but the lead rubber bearing is elastic in the beginning, and then it yields, and it shows an inelastic behavior. And due to inelastic behavior, we get a hysteresis loop, large hysteresis loop, and energy dissipated is depending on the area of that hysteretic loop. So the behavior is going to be something like this. Initially, the lead core is elastic, and the stiffness comes from the rubber as well as the lead. So initially lead core is elastic, then lead core yields, and after that only the rubber pad is providing the stiffness. So stiffness doesn't become zero. Still stiffness is there, and the elastic pad is active in providing the stiffness. So hysteretic loop we will get like this, and we can idealize this. We can simplify this by this parallelogram. So area of this parallelogram is going to give me the energy dissipated per cycle, and then I can join the origin with the extreme point and the area of this triangle which will form here. That will give me ES naught, and 1 upon 4 pi ED by ES naught, I can get the energy dissipated. So this bearing now, in addition to providing flexibility, it is also providing energy dissipation, enhanced damping. And then we have to keep in mind, we want the structure to be flexible during earthquake, but we don't want our structure to be flexible during wind. So we have to ensure that this lead core should not yield under wind, because if it yields under the wind, it will lose its resistance. And because wind load is sustained loading, at least for hours, it is going to be there. So it will cause continuous deformation and failure of this bearing. So we have to ensure that these bearings should not yield under wind, and these will yield only under earthquake forces. Sometimes we use special devices like fuse. So those fuses are active till the wind load capacity is required, and after the wind load capacity is adjusted, those fuses will break. And for example, during earthquake, when the larger force is coming, those fuses will break, and then this device will come into picture. Normally, the yielding capacity of this lead core should be selected in such a way, if we are not providing fuses, that it should take care of the wind force elastically. And when the forces higher than wind force, that means during earthquake, are coming, this should yield and it should dissipate the energy. So when it will yield, it will provide flexibility, and at the same time, it will also dissipate energy. Then a friction bearing, friction itself can be used for energy dissipation. So for example, here we have the typical friction bearing which we were having, the sliding bearing. So the sliding bearing will also have a hysteretic behavior. Okay, I have not shown that here, but this will also have a hysteretic behavior. We can compare it with the previous one. So initially the stiffness will be very high till the sliding occurs. Once the sliding occurs, this curve will become flat. So it will be stick slip type of model. Initially the stiffness will be very high, and contrary to this, here this will become flat. So if I have a flat friction surface like this one, I will not get any restoring capacity, the one I'm having here. So even after yielding of the lead core, we can see here the stiffness is not becoming zero, because the elastomeric pad was active. But when I'm using friction, it can provide hysteresis, I can get energy dissipation, I can get flexibility, but restoring capacity will not be there. So we need the restoring capacity also. That's why most of the times we are not using the flat surfaces. And if we are using flat surfaces, flat slider, then we have to use some additional device along with this, which should bring it back to the original position, or what we call, it should provide restoring capacity. So this value of friction is a little bit tricky. It changes with the value of the normal force. So we can see here, these are some experimental results. So we can see that at slow speed, This pink color is there, and this blue color is sticking. That means when it is not moving. So the maximum speed, maximum friction coefficient you can get is like this, and you can see that both under speed as well as under slow speed as well as under sticking condition, this is reducing with the vertical force. So as the vertical force increases, the coefficient of friction reduces. So coefficient of friction is not constant. It again depends on many properties. So we have to take those into account. And this stick slip behavior, when this type of bearing is subjected to earthquake loading, we are going to get this type of behavior. So when it is sticking, it will come back, and when it is sliding, it will go horizontally. But you can see here that the load displacement curve is horizontal, whereas in the previous case those were inclined. So those were having some stiffness. It is not having any stiffness, so it can provide a lot of energy dissipation, but it does not have restoring capacity. And what may happen during earthquake, there can be permanent displacement, and that permanent displacement will go on adding in under each cycle, and it may be such that it may cause unseating. The permanent displacement, the total accumulated displacement may be more than the displacement capacity which we have designed for. So that's why this type of devices are very useful, but not used alone. These have to be used along with some restoring device. Now, one of the ways of causing restoring force is by making this sliding surface concave. So if I have a concave surface like this, so this is a concave smooth surface, and on that this articulated uh, slider is moving. So when it moves, it will cause a horizontal component, and that horizontal component will cause restoring. It will bring back to the original size. And again, the size of these bearings can vary. So these can be small bearings, and these can be as large. You see, as compared to the human figure, how large these bearings are. So we can have very large bearings with this smooth surface and with a special type of coating, and this slider will move on that surface, and at the top of the slider we are going to place our superstructure. So it can move, it can accommodate very large displacement. So I told you that increased period will cause large displacement. So this radius of this should be sufficient. Sorry, the radius will take off. This radius will take care of the post yield or post sliding stiffness. So steeper the slope, that means smaller the radius, more restoring capacity it will have. And the size of this bearing, the horizontal diameter of this bearing will be based on the total displacement which is going to occur in my structure during earthquake. So that I can compute, and that will decide the size. Now the behavior of this type of bearing is like this. Initially it is in stick condition till friction starts. The stiffness is very high, and once the stiffness, the sliding occurs. So sliding will occur at mu into W, where mu is the friction coefficient and W is the vertical load, and then it will follow this path. Load displacement will follow this path. So you can see it is having a post sliding stiffness also, and that stiffness, the slope of this curve is W by R. So it is inversely proportional to R. Larger the R, smaller will be the slope, smaller will be the stiffness. So larger R means flatter will be the surface. So if R is infinite, that means the surface is flat. This will become 0. So the slope of this line will become 0. It will become flat. In that case, there is no restoring capacity. If we reduce R, the restoring capacity is going to increase. So depending on how much restoring capacity is required, how much total displacement is required, we have to decide this value of R. R will control the design. Now, with this background, how we can design the isolator. So whether it is a bridge or building, when we are designing the isolator, we have to follow some iterative steps. And what are those iterative steps? That first we have to select the size of the isolator. And size of the isolator will be selected based on the vertical load it has to transfer. So let's say there are number of bearings in a small span bridge, then the size is going to be small because the vertical load transferred by one bearing will be small. But suppose I have a very long span bridge, let's say cable stayed bridge, and I want to provide isolation to that. So long span bridge, and there are just two bearings on each side. So the force to be transmitted, the vertical load to be transmitted per bearing is going to be very large. And if the size will depend upon that vertical force. So for transferring larger vertical load, I need larger elastomeric pad if I'm using elastomeric bearings. So, or if I'm using sliding surface, so then my contact should be large. So size will come from there and also from the period. So the period of isolator, we will decide whether I want to give it 2 seconds or 3 seconds, depending on the economy. Because if I increase the period, the earthquake forces are going to reduce, but the displacement will increase. And in that case, I have to design a larger isolator. So using economic considerations, I can decide which period, and then corresponding to that period, there will be displacement. So displacement will decide the size of the bearing isolator. So based on iterations and economic considerations, I can decide that what period I want, and corresponding to that, what displacement I am going to get. So once the size is fixed, I can have a load deformation behavior or hysteretic behavior of that bearing I can prepare. So once that hysteretic behavior is prepared, I can calculate effective stiffness and equivalent damping. So effective stiffness is nothing but joining the origin with the point corresponding to this displacement, design displacement. So that secant line will give me the effective stiffness, and equivalent damping I can calculate using that formula 1.4 pi ed by es naught, which I discussed. So the equivalent damping and the effective stiffness will be obtained from there. Once I know the effective stiffness and equivalent damping, I can read the response of my structure from the response spectrum. What I have to do, I have to use the period corresponding to effective stiffness, and I have to use equivalent damping. So that reduction factor for damping, I have to apply on that response spectrum. And then I will use this elongated period. That will give me the forces, and I can also calculate the displacement. I can also read the displacement from displacement spectrum. So I can calculate the displacement, actual displacement, and this actual displacement I will compare with the original displacement, which I have assumed. So whether these displacements are same or not. If not, I will again change it. And for this calculated spectrum, calculated effective damping and stiffness, I can calculate the design forces using the design response spectrum. And if it is different than what I have assumed in the beginning, then I can revise it, and again I can calculate the revised damping and estimated displacement. I will continue this till it is covered. That means the assumed displacement, the selected size and period and displacement, and what I am getting after the calculation using response spectrum, both match. So it is a simple manual calculation, not very complex. The complexity will arise when we are going to verify this using nonlinear analysis. But for the initial design, nonlinear time history analysis is not necessary. That can be done using simple hand calculations. So these steps are like this, that based on the size of the damper isolator, I can plot the load displacement curve, and then I can generate this corresponding hysteretic curve by assuming the idealized behavior. Actually, you have seen that these corners were not sharp. These corners were rounded like this. So actual area of the hysteretic loop is going to be slightly less, but I can idealize this using a parallelogram. So based on the area of this parallelogram, I will get the value of ED, and then ES naught I will get as the area of this triangle here, and I can calculate ED by 1/4 by ED by ES naught as the equivalent damping. Okay, so effective stiffness I can calculate like this: Kp plus Q by D. It is just the geometry from here. So Kp is the stiffness of post yield load displacement behavior. So this stiffness, the reduced stiffness after yielding, this is Kp, and the effective stiffness is the slope of this line. This is the effective stiffness I am calculating. So this effective stiffness I can calculate as Kp plus Q by D. Okay, so Q is the strength at which it is yielding, or the strength corresponding to the zero displacement. So if this curve intersects here, this value is Q, and Fy is the strength corresponding to yielding. So Q is the intercept of this post yield curve at the y-axis. So that is Q. In terms of Q, dy, I can calculate everything including beta factor. So once I get the beta factor, I can calculate the displacement which it will undergo, and then I can calculate the base shear simply multiplied by the stiffness, the effective stiffness into this displacement. And the design shear force, I can consider this base shear, elastic base shear which I am getting divided by response reduction factor. Now in case of base isolated bridges, the response reduction factor is to be taken as 1. Recently this IRCSP 114, the chapter 10 is getting revised. So when it has been revised, it has been decided that the bridges will be designed for response reduction factor 1, and not only response reduction factor will be used 1, the normal importance factor will also be used as 1.5. So normally the this importance factor varies from 1 to 1.2 to 1.5, but it is assumed that base isolation we are going to use in case of important bridges, and their importance factor should also be used as 1.5. So we can calculate the effective stiffness in case of a bridge. There can be multiple bearings at any end, maybe 2 or more than 2 also. So there will not be a single bearing, there will be multiple bearings. So effective stiffness of all the bearings at one pier can be calculated like this. So we will calculate K effective as summation of K effective I. So I stands for IS bearing. So depending on how many bearings are supporting one span. So a superstructure, one portion of the superstructure which is acting as rigid will be supported by n such isolation devices, and I sum up stiffness of all those n isolation devices. So I will get K effective, and then I can calculate this I effective using 1 upon 2 pi ED over K effective DCD square. So this DCD is the design displacement. So I can decide a design displacement in the beginning, or I can decide a period in the beginning which will give me this design displacement. An effective period I can calculate as 2 pi md over K effective. So md is the seismic weight or seismic mass to be more precise. So it is seismic mass of the superstructure. So in this case, in case of bridges, the base isolation is provided between the pier and the superstructure. It is provided at the bearing level. So the mass which is effective is above the bearing. So whatever mass is there at above the bearing level, that mass we will consider as MD. And K effective is the combined stiffness of all the bearings and the support. So in this case, support is the pier, or it can be an abutment. So the pier and all the bearings are in series, whereas all the bearings together are in parallel direction. So stiffness of all the bearings will be added directly, and then it will be combined with the stiffness of the pier in series. So that is going to give us the K factor. Then we will calculate this factor eta effective. Eta effective is the damping factor. So whatever damping we have obtained here, corresponding to that damping, we will calculate this eta. How we can calculate eta? There is this simple relationship from Eurocode. So eta effective is 0.1 divided by 0.05 plus xi effective, square root of the whole, and it should not be greater than 0.5. So we can see as the effective damping is increasing, so this eta effective is the reduction factor in the response spectrum. So that reduction factor will go on reducing. So but it should not be less than 0.5. So we cannot have reduction more than 50%, and it has been seen that the damping is effective only up to 30%, and corresponding to 30% we get an amplification factor of 0.5. If the damping is further increased, we will not get much advantage. So it is recommended by the code that the damping should be limited to 30%, and then this damping reduction factor will be limited to 0.5. So if we get this eta spectral acceleration, we will read from the code, design code. So in our case, that is Z by 2 into SA by G into R by I into G. So R and I both are one here. So it will be Z by 2 into SA by G into G. So much will be the spectral acceleration. That multiplied by eta effective will give me the SE, the effective spectral acceleration. And this effective spectral acceleration I can use in calculating the base shear. So base shear is the mass into effective spectral acceleration, and that is also equal to the same thing will be because it is just a substitution, K effective, that is the effective stiffness, into the design displacement. And design displacement DCD will be calculated like this. So this is value of SA into damping factor, then into G, and then T square by 4 pi square. So this is nothing but SD. So from this SA, we are calculating SD, and this is calculated corresponding to DBE, because we will be using a load factor of 1.5 above this. So that's why this corresponds to DBE. So a load factor of 1.5 is applicable on this. Then eta effective will be, I already told, and then the base shear can be calculated like this. Now, coming to the displacement. So the displacement which we will be calculating for the isolator, that displacement I will calculate. So this is the displacement requirement or displacement demand. Gamma ys is an amplification factor, and dBID, this is the dB level displacement which we are obtaining for each device. So this is to be multiplied by another factor, another amplification factor of 1.5. Now what is this factor of 1.5? Because when we were designing our superstructure or substructure or even the isolator, we were designing it for dB. But actual earthquake under which we want our structure to remain safe is MC. So forces are calculated for dB. It is designed for dB, but the displacement is to be calculated for MC. And here we have already considered a factor of 1.5 as the importance factor, and the ratio between dB and MC is 2. So 1.5 factor is here. Another 1.5 factor is included here. So 1.5 into 1.5, that becomes 2.25. So roughly it becomes equal to MC. So if we consider this factor, then our displacement will correspond to MC. So we have to keep in mind when we are designing with isolators, so whether it is elastomeric bearing which we are using as base isolator or any other bearing we are using as base isolator, we are designing with R is equal to 1, our structure to remain elastic. But the structure will remain elastic only under dB. Under MCE, the force is going to increase and our structure will yield and some damage will occur under MC. But under DBE, it will be elastic. Okay. And we know that when we are designing our structures to remain elastic with R is equal to 1 using limit state method, and in limit state method, we are using partial factors of safety and we are using characteristic strength. So in that case, there is some hidden strength. So when we are designing our structure to remain elastic under DBE, it will be very close to yield under MC. So damage will not be significant. There will be hardly any visible damage. So that's what the performance we are expecting from our base isolated bridges. But the displacement which is going to occur, that will correspond to MC, and that's why we have to consider this factor of 1.5 so that the displacement is corresponding to MC. Then here we have checked the damping, we have checked the displacement, we have checked the forces. One more capacity we need to check, and that capacity is restoring capacity. So restoring capacity will come from the cyclic load displacement curve of the isolator. So when we are testing the isolator, we will get a curve like this, and we can idealize that curve by equivalent parallelogram like this. And here we can see that when initially the force is increasing or the displacement is increasing, the force goes on increasing because there is some post yield stiffness. Then from here the reversal of the displacement occurs. So initially this line will be parallel to the initial loading line that was somewhere here. It will be parallel to that. But then when the force is removed fully, so at x-axis, so we can see here the force is 0. So when the force is fully removed, even then we see that some residual displacement is there. And this residual displacement, this is of concern. So this residual displacement should be within limit. If this residual displacement is too much, then in successive cycles, this much permanent displacement will be added up and the total permanent displacement may be too high. So to avoid that, the code IRC SP114 and other codes, those codes provide a limit on this D0. So that limit is to be followed. So this displacement, permanent displacement, which corresponds to 0 force, that we have to check. Now, in case of a experimental curve like this, the displacement, permanent displacement, we can see. So permanent displacement, this much is D naught. So this much displacement we have to check, which is occurring under the zero load condition. So under the cyclic behavior, when the load crosses, the force crosses the zero line. So x-axis is the zero force line. So when the load displacement curve is crossing the zero force line, at that point, whatever is the displacement, that displacement is permanent displacement, and we have to check that. So that's all about the bearings, both normal bearings as well as isolation bearings. So thank you very much. I will stop here and we will take up the questions. I think there are some questions, so we will take up. I will stop sharing.
Yes, sir. We have a question from Atikar. Can elastomeric bearings be used without sole plate and base plate? In our country, it is a common practice to use this bearing without sole and base plate. For example, we construct the bearing frame on pier cap, then place the bearing and finally place the girdle of the bearing. There is no anchoring arrangement.
Okay. So without the top and bottom plates, it will work if there is no uplift. So if we are not expecting that in any case there will be a vertical force, in that case it can be used without the plates. And due to friction, it will not slip. But suppose there is an uplift, the earthquake force or the wind force can cause a net uplift on a bearing. In that case, that friction will be lost and it will move freely. The stiffness of the elastomeric bearing is not coming into picture. So we can use it without the top and bottom plates if the vertical load in all the conditions is enough, and that will happen only when the earthquake force is low, in low seismic zones. In high seismic zones, generally there will be an uplift also, and due to that uplift, the elastomeric bearing will get detached from the superstructure. So there it should not be used.
Okay, sir. Mr. Suraj is asking, when elastomeric bearing is provided in the bridge with stopper, do we have to consider the pounding of superstructure with the stopper because of the displacement?
So pounding, whether it is elastomeric bearing or any other bearing, the pounding can occur in any case. So pounding we have to consider. But when we are using elastomeric bearing at one end with stoppers, so there generally a neoprene pad is provided between the stopper and the superstructure also. And in that case, the impact is not very sharp. So the forces can be transferred smoothly from the superstructure to the stopper. Otherwise, we have to consider pounding effect, and we have to design those stoppers for a higher force so that those can take care of the impact also.
I believe you have already answered this question, but Mr. Bharat is asking why in ISC 114 it is stated that if elastomeric bearings are used to transfer seismic forces, the substructure will be designed for R is equal to 1.
Yeah, so in that case, these will be acting as base isolation bearings, and then the substructure is to be designed for R equal to 1 because it will become a flexible structure and the forces transmitted to substructure will reduce drastically. So it is not a big deal to design the substructure for these reduced forces even with R equal to 1.
Okay. Mr. Sandeep is asking, how can we choose the bearings as per load geometry or type of structure?
I mean, the bearings cannot be selected just based upon the loading and type of the structure. There are a lot of options available. So depending on economy, depending on your liking, depending on the skill available, you can choose a number of types of bearings are available. So you can choose, and some of the factors there are subjective. So there is no clear-cut objective criteria by which you can choose that this bearing is best in my conditions. So you should take into account the durability and economy. What is available in economic cost, and we should consider the design life of that type of bearing also.
Okay. Jyoti is asking, sir, do we need to replace lead rubber bearings after major earthquake as a lead core yield?
Yeah, so it will depend on how many excursion inelastic excursion that lead core has gone through and of what magnitude. So if it has undergone large displacements and several cycles of that large displacement, we have to replace it. But if it is subjected to only small inelastic displacement and that too in 1 or 2 cycles, then maybe we can continue. So that decision is to be taken by the post-earthquake inspection and analysis, because how many cycles it has undergone, that is very difficult to obtain by visual inspection. That can be obtained only with some calculation, or if any transducer is placed there, an accelerometer is placed there, then we can find out.
Okay, sir. Okay, this one we have already answered. So just wait a second. Sir, Mr. Jay is asking, at what conditions for bridges can we go with STU to reduce seismic forces?
See, as to you can go when you are using very flexible type of bearing. For example, if you are using, let us say, sliding bearing, okay, and there is no mechanism by which you can transfer the load through the bearing. I mean, that is also true with STU. With this elastomeric bearing. So elastomeric bearing you can use under the normal conditions, under uh, temperature, creep and shrinkage, and wind. You can go for elastomeric bearings. But when it will be subjected to earthquake, it may fail. A lot of failures of elastomeric bearings during past earthquakes have been seen, and that was the reason that some of the organizations they have stopped using elastomeric bearings. So in that case, we may use STU. STU is opposite of the bearing. So bearing allows the displacement, the STU stops the displacement when the displacement is occurring at a very high velocity, like the one which is occurring in case of earthquake. So STU is nothing but a high damping device, and when there is a large velocity, then it will simply provide very high force, or it will act like a lock. So where we expect that the system other than STU cannot transfer the earthquake forces, there we can use STUs.
Okay, sir. Mr. Yogesh is asking, during execution, placing of permanent bearing we generally avoid to eliminate the uneven loading due to superstructure stressing and construction load. So
Hmm.
which type of temporary bearing we can use at the time of this superstructure casting?
Sorry, I don't have idea about the temporary bearing which they are using at the construction. Maybe somebody from field uh, can talk about that, because the design of those temporary bearings is generally not done for earthquake and wind forces. So I'm not very sure that what type of temporary bearings they are.
Okay, sir, I don't see. Okay, this there is a new one also. Lakshmi is asking, sir, how do we make PTFE layer in bearing? I want to know basically know its composition.
Sorry, I couldn't get. How do we make PTFE layer?
PTFE layer in bearing. I want to basically know its composition.
Purpose. Purpose or
What is the
composition?
composition?
Composition. So its chemical composition I do not know. Maybe you can Google and get that how this PTFE is manufactured. But the properties of PTFE is that it acts like a lubricant between two steel plates. It reduces the friction significantly, and that's why we are using it in the bearings, because we want to reduce the friction for the ease of sliding and ease of movement. Okay. Chemical composition, I'm not sure. That can be obtained from a chemical person, or it must be available on internet.
Okay, sir, we'll take the last one, then we'll have a break. Uh, is it preferable to go with bridges with bearings or integral bridges with under seismic conditions? What are the advantages or disadvantages one system with respect to the other?
Okay. So under seismic conditions, it is always better to have redundant structures. So we were discussing that our bridges are determinate structures. Buildings are redundant structures. So in case of buildings, we are having larger energy dissipation, and that's why we are able to use larger response reduction factor. So an integral bridge is going to behave much better than a bridge on bearing during earthquake. But we have to understand earthquake is not the only design criteria. We don't design bridges only for earthquake. Those have to function during other actions also. For example, under live load, under temperature. So if we make integral bridge and the stresses due to temperature movement are very high, then it will fail even before occurrence of earthquake. So the advantage of bridges with bearing, as I have shown in my first slide, bearings are provided with a purpose. If we are not providing that in our design, we have to make provision to resist the corresponding forces. So if I am not relieving the earthquake movement, sorry, this temperature movement, corresponding to that temperature movement, I should calculate forces. And those forces I should use for design in my substructure and superstructure. So both have their advantage and disadvantage. But if we have to look from earthquake point of view alone, then integral bridges are definitely better than bridges with bearings.
Okay, sir, maybe that is all. We'll have a break of half an hour maybe, and we'll join again at 4.
So I see there are some more comments or some of questions that we have left. So we have some time. So maybe we can take up those. So are those questions available to you? Like I can see one from Muhammad Nawar.
Nawar is asking, can we go for higher R factor in case of base isolated buildings or bridges?
No, in fact, in case of base isolated building, we go for R is equal to 1. In case of base isolated structure, we go for R is equal to 1. So purpose of base isolation is not to provide economy. Base isolation is not to be used for economy. Base isolation is a costly device. It is not to be used for economy. Base isolation is used for better performance. So better performance means that the damage in the structure should be less, whether it is building or bridge. So there the response reduction factor is close to 1. Even in case of buildings, it is close to 1. So that our structure, whether it is building or bridge, remains more or less elastic, even during MC earthquake, so that the damage is not much. The building is functional. That is the advantage. So we should never think of using base isolation for economy, so that we can reduce the response reduction factor. Using base isolation, we can reduce the cost. So that is not the idea. The idea is to improve the performance of the structures during earthquake, because our normally designed structures where we are using response reduction factor, their performance, especially under MC, is not acceptable. The damage which is going to occur under MC will be very high, and we can't afford that with our important and costly structures like long span bridges. So there we will like to go for R is equal to 1, not to increase. We are reducing R in case of response, in case of base isometric structure.
Mr. Bharat is asking, it is seen that at the location of bearings, the rubber of elastomeric bearings damaged due to some garbage collection. Is it possible to repair the neoprene of these bearings?
I mean, we can replace the bearing itself. So bearing replacement is possible. We lift the superstructure with jacks and then replace the bearing.
Mr. Bharat is also asking, what is the maximum period which can be allowed in bridges without using dampers and base isolate?
There is no limit. Okay, so code does not provide any limit which you can do, but if you are going to increase the period without providing base isolators, so in that case, the period effects are going to be very large. The displacement will be large and then period effects will be very large. So you will not be able to design it. So there will be practical limits which will come from design, but there is no statutory limits given by code that this is the maximum, like we have in case of buildings, we have interstory drift. So any such criteria of displacement or drift in case of bridges is not available. So it's your choice. You can use any period.
Okay, Mr. Sandeep is asking, which type of bearings have important role for formwork or girdle launching of
Sorry, for from work.
formwork or girdle launching of bridge?
Okay, that was a similar question which somebody was asking the bearings during construction time. So sorry, I don't have that background. So during construction, I can't answer this question.
This is, Mr. Jamet is asking, can a bridge stand without bearing and how for how many years?
Can a bridge span without bearing?
Stand without bearing
Stand
and for
without bearing.
right.
So any bridge you can make integral bridges. Now it is a lot of integral bridges are being constructed. Only thing is there we have to calculate the forces for temperature movement and we have to design our substructure for those forces. So bearings are not theoretically necessary. It is the choice of the designer whether he wants to relieve the forces or he want to resist the forces. So if you want to resist the forces, you have to go for integral bridges. If you want to relieve the forces, you have to provide the bearing.
So Mr. Bhatt is asking, is the use of seismic arresters necessary when transferring forces through elastomagnetic bearings?
So if the bearing itself is capable of transferring horizontal forces, longitudinal case maybe, then stoppers are not necessary. Just as a second line of defense, we use that in extreme case, if our bearing fails, then our superstructure should not get dislodged. But if the bearing itself you are designing for the forces required, then it is not necessary. Necessity comes when we are using neoprene bearings and we don't want the forces to be transferred by neoprene bearing. In that case, it is a must to provide the stoppers. Otherwise, it is our choice. It is second line of defense.
Okay, so Mr. Bharat is asking why the stopper are designed for twice the seismic force when R is equal to 1 U.
Yeah, because actual earthquake which will come is MC, not dB. It will come as MC, and MC is two types of dB. That's why we are, even when we are designing with R is equal to 1, actually we are designing for dB, not for MC. So our displacement demand, which we have calculated DCD, that was for dB. So MC displacement demand will be two types of that.
Yes, sir. That was all of the questions.
Okay. Okay, so I hope we have answered most of the questions, at least of this session. Maybe some questions of the first or second session may be remaining there. We will take up those through email. So thank you. I think we can stop here and then we are meeting at 4?
4. Right. Yes.
Okay.
At 4 will join for hands on set.
Okay. See you. Bye bye.